4.14. Many people start their day with a jolt of caffeine from coffee or a soft drink. Most experts agree that people who consume large amounts of caffeine each day may suffer from physical withdrawal symptoms if they stop ingesting their usual amounts of caffeine. Researchers recruited 11 volunteers who were caffeine dependent and who were willing to take part in a caffeine withdrawal experiment. The experiment was conducted on two-day periods that occurred a week apart. During one of the periods, each subject was given a capsule containing the amount of caffeine normally ingested by that subject in one day. During the other study period, the subjects were given placebos. Okay, so capsule and placebo. The order in which each subject received the two types of capsules was randomized. Okay, so the order was random. Subjects received both types. So I can already tell this is a matched pairs design. Right, since each subject is receiving both treatments just in a random order. All right, the subjects' diets were restricted during each of the study periods. All right, so I think the idea here by restricting their diets is to control for the effective diet, right? We don't want the diet to become confounded with the effect of the capsules. Subjects were evaluated using a tapping task in which they were instructed to press a button 200 times as fast as they could. Okay, so that sounds like the response variable. How long it takes them to press the button 200 times, so the tapping task. All right, part A, identify the explanatory and response variables in this experiment. Okay, so the explanatory variable is the two capsules, caffeine and placebo. So the caffeine, how do you spell caffeine? Caffeine, capsule, and the placebo. Okay. The response, I'm going to guess, is the time it took them to complete the tapping task. Time to complete tapping task. Okay. All right, that's part A. Part B, how was blocking used in the design of this experiment? What is the benefit of blocking in this context? Okay, so in a matched pairs design, right, in this case, each subject is paired with themselves, right? So they are their own block. Each subject is their own block. Okay. And so by blocking or pairing each subject with themselves, we should be able to reduce confounding due to other factors like age, gender, height, weight, whatever. Yeah, okay. So this will reduce confounding with other factors such as age, gender, weight, etc. Right, because we're only going to compare one subject's result with their other result, right? I'm not going to compare Bob's time on the tapping task to Sally's time. I'm going to compare Bob's time to Bob's time because he's going to do it twice, once with the caffeine capsule and once with the placebo. Okay, so it's really to get this apples to apples comparison and not having any other differences between the measurements that you're comparing, such as age, gender, weight, etc. Another thing I can think of, which might be the answer they're looking for is that it also reduces the variability, because now I'm only looking at Bob's results, which there's going to be much less variability when I'm looking at Bob's results than when I'm looking at everybody's results together. Okay. All right, let's look at part C. Researchers randomized the order of the treatments to avoid confounding. Explain how confounding might occur if the researchers gave all subjects the placebo first and the caffeine second. In this context, what problem does confounding cause? Okay, so if you give the caffeine second, then that measurement already has a slight advantage, because now that measurement could be better for two reasons. Maybe the caffeine made the second measurement better, or maybe the fact that it's their second time and they already had experience doing the tapping test the first time, that now that second measurement is better. Okay. So second measurement has a slight advantage due to the fact that the subject had experience from the first measurement. Okay. So the confounding occurs because now if there is an improvement, we don't know if it's because of the caffeine or because of the experience. Okay. So therefore, if there is an improvement, we don't know. If it was due to the caffeine or the experience. In other words, we cannot isolate the improvement to the caffeine. It could be some other reason, right? Now there's something that's systematically different in all of those second measurements, which is just the experience that subjects get from doing the same task a second time. All right, could this experiment have been carried out in a double-blind manner? Explain your answer. Okay, so yes, if one, the capsules are unlabeled, okay, so now the subjects don't know which treatment they're receiving, and two, if the person who is evaluating the tapping task, if that person doesn't know which treatments the subjects received. All right, so yes, if one, the capsules are unlabeled, and two, the evaluator doesn't know which subjects received which treatments. All right. Now, the reason why we don't want the evaluator to know is because we want them to record the data honestly, right? So if they're like having a stopwatch and they're timing, how fast it's taking these subjects to complete the tapping task, and let's say they know that the subject was on caffeine, right? We wouldn't want them to perhaps round down the time on the stopwatch due to the fact that, oh, they know they had the caffeine, let me round this measurement down, or vice versa, round the number up because they know that they were on the placebo, right? So we don't want to introduce any bias in the data measurements due to knowledge that the evaluator has.